Welcome back to part 2 of our introductory lesson on trigonometric identities. Recall that in part 1 we proved the quotient identity, that is that tan theta is equal to sine theta divided by the cosine of theta for all values of theta. Now we move forward in proving what is called the Pythagorean identity. Okay, this one right here, which is referred to as sine squared theta plus cosine squared theta equaling 1. One thing that we should take note of is the representation of this or of these quadratic trigonometric expressions. They're written differently, and to avoid confusion, what I would like you to take note of is that when we write sine squared theta, I just want to make that clear that it is not equivalent to sine theta squared. I sometimes get the question, why is the square where it is? Okay. In the right-hand expression, having the square on the angle means that theta is squared first, and then you would take the sine of that particular answer. Whereas on the left-hand side, it's not theta that's being squared, but rather sine squared theta is equivalent to the sine of theta multiplied by itself. Okay, so the placement of the exponent allows us to differentiate between these two different representations. One being the correct one, that's the bottom one, and the top one not being the correct representation. So moving forward, let's have a look at this Pythagorean identity, and our task is to prove it. So let's begin our formal proof by separating the left side from the right side. Okay, so in order to prove this identity, what we should be doing is having a look at earlier established identities. And namely, you can see that I've got the two definitions of sine and cosine over here to the right-hand side. And it's our job to use those expressions. Okay. The most natural thing to do would be to substitute y over r and x over r in for the value of sine theta and the cosine of theta. But what we're going to do is we're going to approach this slightly differently. Okay? So I'm just going to draw these expressions over here, and we're going to have a secondary or intermediate part to our solution. What we're going to do is we're going to solve for both y and for x in terms of r and sine or cosine theta. So in this case, if we isolate the y, we'll see that it is equal to r sine theta. Okay. What we'll do on the right-hand side is the same thing. We'll solve for x, and we'll determine that x is equal to r, the radius, times the cosine of theta. Now, notice what we have in the equation. Okay. Both the values of sine and cosine of theta happen to be squared. Okay. So what we're going to do is we're going to draw upon the idea of Pythagoras' theorem, hence the reason why it's called the Pythagorean identity. And what we'll do is we're going to determine the sum of the squares of both x and y. So we're going to bring these two pieces together. So the expression x squared plus y squared, okay, is going to end up being equal to r sine theta squared plus r cosine theta squared. Notice that the terms have been written down in a different order, okay? Because the second expression corresponds to x, whereas the first expression corresponds to y. So if we move forward with this new expression, okay, we're going to see that we end up with r squared multiplied by sine squared theta plus r squared multiplied by cos squared theta. If we continue our work on the right hand side, what we're going to notice is that both terms contain an r squared. So we're going to factor out r squared from both terms. Okay. So what I want to now draw you back into is this particular definition here on the left-hand side. X squared plus y squared. It just so happens that if we were to circle back or to go back to an earlier part of the lesson, and I think it's a great time for us to do that. If I go back to an earlier slide, and I'll have to apologize as I did not keep the material that was there, what I want you to notice is that with our circle that we had drawn earlier, and the right angle triangle that had been inscribed inside of that circle, we had noticed that for any coordinate, right, x comma y, that the following relationship is true for this right angle triangle. With a base length of x and a height of y, we know that the relationship, the Pythagorean relationship, is x squared plus y squared is equal to the square of the radius. So think about where we've seen this before. In our current proof, we have that very same expression. Okay? So what that means is that we can now substitute the value of r squared into that because of the Pythagorean relationship. We'll set that equal to the right-hand side. And then look at both sides, and you'll notice that there are some common factors. If we were to divide both sides by r squared, the r squareds would cancel, reducing to 1 over 1. And hence, what we can see coming out of this is that 1 is equal to the right-hand side, sine squared theta plus cosine squared theta. So we've proven the fundamental Pythagorean identity using a slightly different approach. Okay? In an earlier proof, we had previously established facts and we solved things kind of deductively. But we're sort of coming at this from a different perspective, that we're making inferences as we go through. So it's almost like we're proving this inductively. Okay? So what we'll do is we'll make a formal conclusion based on what we have here thus far. So as I'm running out of space, I'm just going to extend the page. So since, well, given what we have, it's not that we can say that left side is equal to right side, as our approach to this solution greatly differs from what we've seen before. Okay, so we're going to, at this point in time, we're going to adopt the current scheme that we have here as proof for the Pythagorean identity. So based on this, therefore, sine squared theta plus cos squared theta is equal to 1 for all theta. Last but not least, before we see some examples in tomorrow's class, we should look at some variations on this identity. Okay? So for instance, given that we've proven this, it also makes sense that we can isolate the sine squared theta term by subtracting cosine squared theta from both sides. So we now have an equivalent expression for sine squared theta that we could use when proving identities. The same thing exists for the identity below. We could very well isolate the cosine squared term by subtracting sine squared theta from either side, or from both sides. And now that we have an equivalent expression for cosine squared theta, we could substitute that in when we're working in proving other trigonometric statements as being identities. So when you come back to class tomorrow, what we'll do is we'll review a few tips or key steps for proving trigonometric identities, and then we'll actually begin the process of doing our proofs.